Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so let's get started. We're very glad to have Chen Hua here visiting with us. He's currently a graduating PhD student at Stanford University working with John Mitchell's group on wireless security. His research interests are to address the practical security problems in complicated computer systems, and he's really interested in real-world vulnerability and exploit. Before joining Stanford, he got his master's degree from University of Hong Kong and a bachelor degree from Tsinghua University. Chen Hua.
Okay, thank you. Thank you for introducing me.
Turn on the microphone.
Oh yeah, I think.
No, it's not down. There's a switch there. Yeah. Ready?
Yeah, I think.
Down. Okay.
Yeah. Okay. Good morning. My name is Chen Hua. Today I want to talk about 802.11i security analysis. This work was done with Professor John Mitchell at Stanford University. As you might know, security has been a serious concern in wireless networks. So people are questioning about one problem. Can we build a secure wireless local area network? In this talk, I will try to answer this question. My talk will be divided in as follows. First, I will overview the wireless local area network security. Then I will describe the details of 802.11i standard. Then our goal is to analyze this standard. We will use finite-state verification to analyze the components. We found some vulnerabilities in the four-way handshake. We propose the solutions. The vulnerabilities and the solutions are actually very simple, but it was a vulnerability and it can launch a very easy attack. So the standard committee adopted. We also found more insecurities and improvements to the 802.11i. I will talk about the details later. Finally, we conduct a modular proof of the security. Here is the example to show the 802.11 infrastructure network. Generally, there will be an access point connected to the web network or internet. There will be some wireless devices like laptop, PDA connecting to the access point. But the problem is, since the wireless radio is open to the public, anybody with a moderate equipment can listen to this traffic and interview with the traffic. Even worse, if people can make the antenna by himself from some very cheap parts like the empty can and some parts you can buy it everywhere, then it can enlarge the coverage of the wireless radio. So a real concern is, can we build a secure wireless local area network? In order to answer this question, first let's clarify what the threats on wireless network. First is that very intuitively is the passive eavesdropping. Passive eavesdropping means everybody can eavesdrop the traffic in the network. That's very easy since most wireless network interface cards have promiscuous mode. Also, message injection and active eavesdropping is very easy, since there are some techniques to generate any packet format and any packet content with a common wireless card. And also, since the MIC protocol is designed to be cooperative, so that an attacker can interfere with the traffic in a very timely way. On the other hand, the message deletion and interception is a little bit hard, but it's still possible. An adversary can interfere packet reception process in the receiver side by using a directional antenna or using a stronger power. Of course, masquerading a malicious AP is very easy, since the access point, there's some software to install the access point in a regular network card, and the MAC address is forgeable. There are also some other sophisticated attacks on wireless networks, like session hijacking, man in the middle, and denial of service attack. So in order to defend against all of these threats, people are trying to find some security solution for wireless network. Originally in 802.11, they use a wide equipment protocol to achieve this goal. They have some authentication protocols like open system authentication and shared key authentication. Some vendors also use some MAC address filtering to do authorization. And there are some confidentiality and integrity protocol, which is a stream cipher RC4 with CRC. However, since 2000, this was found completely insecure. So people are trying to improve this and solve the problems. Wi-Fi Alliance proposed this WPA protocol. In WPA, they use 802.1x for authentication, and they use TKIP for the confidentiality and integrity. I don't want to talk about the details of these protocols, but the problem is they want to reuse a legacy hardware from web, so there are still some problems. Also, availability is a big problem. A very straightforward denial of service attack is frequency jamming. But this is inevitable, but this is expensive and this is detectable. So we don't consider this except for the military application. Also, there are some possible attacks from the network and upper layer, but that depends on the protocols. So our focus is on the link layer. Unfortunately, there are also many denial of service attacks on the unprotected management frames at link layer. So we have learned there are many threats on the wireless networks, and people try very hard to achieve a secure wireless network. Now, but all those solutions have vulnerabilities inside them. So the latest 802.11i standard are trying to eliminate all of these vulnerabilities. 802.11i was ratified on June 24th, 2004. It provides data confidentiality and integrity through encryption, decryption in the link layer. It also include WEP and TKIP for backward compatibility. It introduced a new algorithm called CCMP, Counter Mode CDC MAC protocol, as a long-term solution. But this long-term solution will need hardware upgrade. So we won't analyze the detailed encryption decryption algorithm, but we believe with the fresh key 802.11i CCMP is secure. So since CCMP is used AES cipher, and there are many studies on AES already. Our focus is on the mutual authentication protocol and the key management protocol. Actually, 802.11i is quite secure in its original version, but there are still some subtle problems, and the solutions are very easy. So here I will describe the 802.11i in details. 802.11i adopts RSNA, which is Robust Security Network Association for the security. The RSNA establishment procedures contains many stages and many message exchanges. I will discuss it later. So our security analysis gives out this can provide satisfactory authentication and key management. But as we say, there could be problematic in transient security networks, and there are some reflection attack on the four-way handshake. Also, availability is a big problem here. So here is a complete conversation of 802.11i. In 802.11i, there are three entities involved. Firstly, the supplicant. The supplicant could be any wireless device like a laptop or a cell phone or something like that. Another one is the authenticator. The authenticator is basically implemented in the access point. There are also the third entity is authentication server. This authentication server could be implemented inside the single device with the authenticator, or it could be implemented in a separate backend server. If it's implemented in a separate server, we assume the connection between them is secure. So at the very beginning, the supplicant wants to talk to the authenticator. they will run an 802.11 association to set up a physical connection between them. Then after this physical connection set up, the authenticator will act as a relay, and the supplicant and authenticator will run a mutual authentication protocol to mutually authenticate both sides. This mutual authentication protocol we assume is IEEE. After the mutual authentication protocol, the server has shared some key with the supplicant, which is MS key. Then the server will move this MS key to the authenticator, and the authenticator and the supplicant will derive a pairwise key from this master session key. So this pairwise key could also be pre-configured or be a cached PM key before. Then with this PM key, they will run a four-way handshake to derive a fresh session key, which we call PTK for the data session. Then they will run a group key handshake to derive the new group key for multicast applications and so on. Then based on the group key and the pairwise key, they will run secure data sessions. Okay. So our goal is to analyze the protocol. Actually, we found some very simple vulnerabilities inside it, but it's ignored, and we propose solution for that. We use finite-state verification to analyze every component of the protocol. But in this talk, I will use a four-way handshake as an example. Finite-state verification is a very powerful methodology. It's widely used in software verifications and security protocol analyses. So the comparing to static analysis and dynamic tracing techniques, it has no requirement for implementations. We can analyze any specification with document. But the challenges is you need to understand the document very completely, since you need to code them by yourself. Another challenge for finite-state verification is the state space explosion problem. We need to reduce the state space. Fortunately, there are already many tools available for us for general model checking and for the automatic model generation model checking. We will use the method model checker. Method model checker uses method rules for every protocol participant and intruder to define a non-deterministic state transition graph. Then every node in this graph will represent some state, and method will exhaustively enumerate all graph nodes. If there is some security property violated in the graph, the method will verify this node, and the path from the initial state to this node might construct an attack. Here is a figure to show how we do these things. First, we have the informal protocol description. This could be RFC attribute standard and so on. Then we will have a method code to build up the formal protocol. Of course, this method code should be different for every protocol. Then we will write the method code for the intruder. The method code for the intruder could be similar for every protocol, since the intruder will have the similar capability. Then we will let method specify the security conditions and let method run. And method will find some error. Then we will diagnose this error. Unfortunately, in most of the cases, the errors are caused by bad abstraction. That means we remove too much detail from the protocol when constructing the abstracted model, and in this way we will add the pieces in and run the method again. By repeating this process, we can find some genuine attack. That will be our NAC. So the attacks found by formal analysis are usually very strong, since it's independent of the cryptographic schemes and independent of the implementations. It's not a software problem, it's a problem of the protocol itself. If available, we can also test this attack on implementation. So here is what we do with the four-way handshake. The four-way handshake recall that the forward handshake will have some PM key pre-shared before that. Then they will run the forward handshake to exchange some random number and derive a fresh key. So that's simple, and the protocol seems very good. But there are some vulnerabilities inside it. We use the follow rules to model the forward handshake. The authenticator and the supplicant will maintain an association, and each association has a uniquely shared PM key. And there might be multiple sequential sessions in one association. For the intruder, it can impersonate both supplicant and authenticator. It can eavesdrop, intercept, and replay messages. It can compose messages. It can forge message, or it can predict and replay lengths. So the environment we want to check for the security represents the security property. It must be true for each state. So here is the example for the authenticator to sending message 1 in method code. The authenticator, if the basically method code is some rules. So if the authenticator is in some state, it will do like shown here. This is if the authenticator is in some state, it will do the following actions. So that's basically a method rule. We need to program every rule, every entities for every state in the system, and then for the protocol. That means we need to understand the protocol previously. This is the security properties we want to check. What we want to check here is the PT key are consistent and fresh. So unfortunately, or maybe I should say fortunately for our research project, we found some easy attack on this protocol. And the solution is easy, and but it's a tricky program. So here is the forward handshake. The supplicant and the authenticator will exchange the first message, which with a random number inside it. Then the supplicant will derive a new random number and derive a new PTK and send out the new random number with the message protected by the message integrity check code. Then the authenticator will check this message and finish this protocol. So the basic attack is the adversary can send out this message after this forward handshake finish. Then upon receiving this message, the supplicant will derive a new random number and then derive a new PTK. And then the supplicant will have an inconsistent PTK with the authenticator. So the protocol is blocked. The designer of the protocol, the designer of 802.11i seems to notice this problem already. So they propose a solution to this, which is they use a temporary PTK to store the temporary PTK in this forward handshake. And the temporary PTK is copied to the PTK only after this third message is verified. That means when the supplicant got this message, it will never affect the PTK. But the problem is we have seen that the adversary can interfere with the traffic in a timely way. So the adversary can send out the message 1, forged message 1 in this point. Then it will change the temporary PTK. But since this leak is computed in the temporary PTK, and I don't know what's wrong with this, maybe. So the PTK here will be the temporary PTK here. But after this, the temporary PTK has changed, so the supplicant cannot verify this message. So it's very easy, but it's a subtle program. The only way for the supplicant to be able to finish this protocol is the supplicant must store all the states of all the incoming message 1s and PTKs derived. Of course, this causes a denial of service attack, which the adversary can send out a bunch of message 1 then to fill up the queue in the supplicant side. For For a simple computation, we can calculate this method. The number of these kind of messages in an 802.11b network could be very large. Is okay.
I mean, if I just send out the garbage there, then that's going to interfere with those messages. That's in fact just tampering with usual bits to make the mix not work. It suffice to compensate task, isn't it?
Yes, but you need to send out a lot of message, which is which might we might jam in the frequency or something like that. But for this one, we can only send one message. Then the protocol is blocked.
Right. If I simply send it, okay. Okay.
Yes. Okay.
I think I lost I'm lost on the exact meaning of the PK. What is the scope of this shared key as opposed to the PM key?
The PM key could be derived from a mutual authentication protocol, or it could be pre-configured to a device, or it could be used as cached PM key from previous associations.
Is it assumed to be a shared secret between the two?
Yes.
Okay.
But they want to derive a fresh secret from this for each session.
Are they using the PMK to sign these messages that they exchange? The boot
They're
messages?
signed.
They're not signed.
The way they use it is they derive a PTK from this PM key. Then use some part of the PTK to compute a hash, a keyed hash of the message. So this is so a very simple solution to this is actually we propose 4 solutions to this. The last one was accepted. So the very simple solution to this is we can just use a random drop queue. The supplicant can randomly drop a stored entry to adopt the states for the incoming message 1 if the queue is filled. But the calculation shows this solution is not so good, since the horizontal axis is the number of malicious messages, and the vertical one is the probability of the protocol being blocked. So with the adversary can send about only 16 messages and block the protocol with probability over than 80%, even with a queue size of 10. So this is not so effective. The second solution is, since we have the supplicant and the authenticator has already shared some PM key, so they can use that shared PM key to authenticate message 1. Then, in order to reuse the algorithm and hardware, they can set that, since the PTK is derived from PMK and nonces, they can set the nonce to special value like 0, then derive the PTK and use the PTK to verify the message. But this is a good solution if the PM key is fresh for every session. But if it's not fresh, if it's pre-configured or it's cached, then there are some replay attacks. In order to move these replay attacks, we need to add a monotonically increasing global sequence counter. This is simple in the protocol, since we can use a local time in authenticator side. We don't need to worry about the time synchronization. And also there are sufficient space in message 1. The 8 octet is enough for a sequence counter. But there are some modifications in the packet format, so that's not good. The third solution is this is a very tricky one, since the supplicant can reuse the length. Generally not.
Go back to the previous comment.
Okay.
These PMKs are always pairwise?
Yes.
You never have shared ones multiple APs?
Yes.
Okay, so that's why you can, that's why okay, go ahead.
Yes. So the supplicant can reuse the length. Basically, in a security protocol, the length means it must be fresh every time. But here, the supplicant can reuse the length until one forward handshake completes successfully. So it will only store this length for this forward handshake. And it can derive correct PTK from message 3 directly. You don't need to remember message 3, remember the PTK and the incoming length. there is no requirement for the authenticator. So this solution solves the problem. It's a very simple solution, but it costs more computation in the supplicant side, since the supplicants need to compute the PTK at the first time it got message 1, and at the second time it got message 3, you need to recompute it and recompute the message integrity check. So also the attacker might get more information about the PM key. Since if we reuse the length, that means that this S length is constant. So this is the address of the authenticator and the address of the supplicant. And the adversary can control this length. So it might got some information for this PM key. But if the PM key is strong enough, there is no problem here. So the problem is the performance degradation. There are more computations in the supplicant side. So our final solution is a combined solution. The supplicant reuse the length, but it also stores one entry of A length and PTK for the first message 1. So if the length in message 3 matches this entry, we'll use the PTK directly. Otherwise, we derive PTK again and use it. So the advantage of this one is just like the previous one, it eliminates the memory denial of service attack completely. And it can ensure performance in a friendly scenario. Friendly means there might be not too much attacks in the network. And this only need minor modifications on the algorithm in the supplicant, no modifications on the packet format, no modifications on the protocol. So this one is adopted by the task group I. This is a simple solution. Actually, the vulnerability is simple, but nobody found it. The solution is simple, but it's not immediate. Before we got this, we tried many others. So since we are looking for a solution which solves the practical problem, we are not designing a new protocol. So we don't have so much freedom. Another problem for the forward handshake is the reflection attack. Since the adversary and the legitimate device, since the forward handshake use symmetry cryptography primitives for the handshake, so there is a basic reflection attack. The legitimate device wants to communicate with somebody, so it sends out this message 1. But there is nobody there, so just the adversary will just reflect this message. Then the legitimate device will generate this message. Then go on. So during that time, the adversary don't need to generate anything. So it don't need to break into the system. So it just reflects the message. Then afterwards, the legitimate device will think it communicates to some peers which is authenticated, but actually there is nobody there. This scenario is possible in ad hoc networks, since each participant will play both the roles of authenticator and the supplicant. It will cause less damage if strong confidentiality protocols are adopted, since even if the adversary can fool the peers to send packets, it cannot decrypt it and generate responses. But this does violate the mutual authentication concept in the protocol, so we still consider it as attack. The solution to this is we can restrict each participant to play only one role. That means the access point will never respond to a message 1. A wireless device will never generate the message 1. So, but this scenario is inappropriate for ad hoc networks. So in ad hoc networks, each participant can play both roles, but it should be under different PM key. This is a very easy mistake to make, since two devices might share some PM key, and they will run one as authenticator, another as supplicant. But in another session in the protocol standard, another one will run as an authenticator, and this one will run as a supplicant. So they will use the same PM key.
Okay. I don't understand how the reflection attack works.
Okay. The reflection attack works as follows. The legitimate device sends out message 1 to somebody. This MAC address is forgeable. So the adversary intercepts this message, and if you want to respond to this message, you need to generate a new message 2. And this method 2 is protected by the method integrity code. And the adversary doesn't have this, cannot generate this. So it just reflects this method to the legitimate device. Then the legitimate device will compute this method 2 for the adversary.
This is essentially equivalent to a wire attack, where
Yes.
there's a wire, and it pretends to be a wire, and you let two parties work, or people just, and that's a standard thing that you essentially cannot prevent in any protocol, right? I can always stand in the middle and echo back to people back to the, sometimes called a set player attack.
Yeah, but this is not only standing in the middle. There might be there is no devices here. The adversary just plays both rules.
Oh, the same part.
Yeah.
Oh, I see. Okay, if the part, well, okay, there's a variation on that.
Yes.
It's a loop wire attack.
Yes. Yeah.
Okay.
Yeah. So here is the summary for the forward handshake. We use finite-state verification to find very subtle bugs in the protocol, and this proves that finite-state verification is suitable for verifying small protocols. Here I mean I mentioned small protocols because the finite-state verification will face the state space explosion problem. So there are some techniques to reduce the state space, but I will not talk about them in this talk. We found that message 1 is vulnerable for the denial of service attack, and by sending out one message, the adversary can block the whole protocol. Even if the supplicant store all states, there is still a denial of service attack. So the solution to this is the supplicant should reuse the LANs, and this solution is adopted by the standard committee. We also found a reflection attack. This reflection attack requires each entity either place only one rule, like in a wireless LAN scenario, or play both rules and a different PM key in ad hoc scenario.
Wouldn't you expect that? I mean, if, for example, one party is playing both roles, that when somebody comes up with a supplicant, for example, then it would go back to the authentication server and get a new PMK for that pair. And when it plays authenticated in another scenario, in another setting, it would again do the same. But in each case, it would get different PMKs.
Yes.
So you would normally expect that this would.
Yes, but in ad hoc networks, sometimes they pre-configure the PMK into the device. Yeah. So we have done the finite-state verification of all the components. Then another thought is when we combine them together, are they secure? Actually, we found more problems when we consider the whole 802.11i as a whole. So the first one is the RSN-IE poisoning problem. RSN-IE contains the security parameters of the protocol. So the supplicant and the authenticator will negotiate about this RSN-IE at the beginning of the protocol and verify it at the four-way handshake, which is very late in the protocol. So the idea to confirm this security parameters is good, but the method they are doing this is not so good. So as it's shown, the adversary can send out a beacon with modified RSN-IE or send out a proof response with a modified RSN-IE. Then this modified only modify insignificant bits, so the protocol will go. But until the 18th message, the confirmation will fail, since the confirmation is a bit-by-bit comparison. And in this case, the adversary only send out one message or maybe several messages, but the whole system will the protocol failed and the whole system will deassociate. So it's very easy for the attacker to launch the attack, and the legitimate user might not know this. It just continue with the protocol but failed at some point, then restart. So that will waste the resources in the legitimate devices. So the solution to this is, first we can authenticate all the management frames, but that seems difficult to authenticate the beacon and probe response frame. Since the beacon and probe response frame is at the very beginning, there is no secret shared. So another is we can confirm the security parameters as soon as possible. Since basically we cannot eliminate this problem, since at the very beginning, two parties don't share anything. So the problem is we want to improve this by move the security parameters confirmation to as soon as possible. Then it will waste less resources under attack. But this needs some modifications on the standard. So the third solution to this is we can relax the condition of the confirmation. Currently, the condition for confirmation is it will compare bit by bit, and it will fail whenever one bit is not matched. So actually, this is too strict for confirmation. We can ignore the insignificant bits, only confirm the authentication suite. We can imagine if the authentication suite is correct, that means we already do a correct authentication. So we can use the confirmed security parameters after authentication. That will be protected by shared secret. So what happens if the authentication suite is modified? Fortunately, that will cause the protocol to fail immediately. Then it will restart and maybe find a new access point. So that improves the efficiency of the protocol. There is also another security never rollback attack. As we have learned that supplicant and the authenticator exchange the security parameters at the beginning. So suppose the supplicant and the authenticator are both enabled with RSNA and pre-RSNA. Pre-RSNA means the web protocol. So after the protocol, they should be able to set up an RSNA network. So, but if the adversary just forge this beacon message or forge this one, forge either one of them will with the indicators which says only pre-RSNA is enabled. Then the supplicant will choose web pre-RSNA method to connect with the authenticator. That will cause they set up a web connection. But since web connection is insecure, so this is completely insecure. This one is similar to any general version rollback attack. It will destroy the security completely since web is insecure. But I should say it's not a real vulnerability of 802.11i standard, since 802.11i suggests everybody to use RSNA. But it's a real vulnerability since it also suggests TSN means implementation of TSN. TSN means transient security network. So that means people might want to migrate from the web protocol to the most strongest protocol in 802.11i step by step. Then there might be some period which has both web protocols and RSNA protocols. So that's a problem. And the user might, and the administrator of the network might want to don't let the user know what kind of thing you are doing. So we just do it transparently. So that's a problem. The solution to this is we can allow only RSNA connections. This is secure, but it's too strict. And in most of the case, I believe TSN will be the reality in some period. So the second solution is we can adopt both, but the supplicant must manually choose to deny or accept a connection. And the authenticator can restrict the web connections to only insensitive data. Actually, we have used this in the current network. That means if you are trying to connect to a network, you always have choice to select is insecure. Would you want to proceed? But the problem is if we already use web and we want to migrate to the stronger authentication, we also need user to choose, since web is completely insecure.
I have a question. about that.
Okay.
Why not? It sounds like the protocol is strictly message driven. Like when I receive a message, I assume that's authoritative and then I respond to it.
Yes.
Why not have just a period of time under which I listen for messages, and if I get two, one that says RSNA and one that's pre-RSNA, I prefer the RSNA one.
Okay. Yes, that's another. Yes. Actually, the problem with this is first the adversary can control the message. We have said it can insert the message in a timely way. So you cannot. You don't know how long you got this message, and you don't know whether you got several messages from the adversary, then a genuine message, or the genuine message, then several forged messages. You don't know anything about that. So you can wait quite a long time to get this, but that will reduce the performance, obviously.
So it's not also possible that you can track a second message so that you get the message?
Oh yeah, it's possible. Yeah, it's possible, but that. Okay, let's move on. There is also another attack on the micro countermeasure mechanism. This is on the TCP protocol. TCP uses a microalgorithm to compute the message integrity code. And the microalgorithm, since it wants to reuse the legacy device, so the microalgorithm will only provide 20 bits of security due to the limitation of the computation power. 20 bits of security means in an 802.11b network that an adversary can make a successful forgery every 2 minutes. So obviously that's not good, so we need countermeasures. The documentation proposed the following countermeasure. First, we can cease the communication for 60 seconds if two failures are detected. Then we can rekey and deauthentication. Of course, rekey and deauthentication is not a good solution. They have discussions on this, and they are going to disable this. So since rekey and deauthentication will leave more time for the attacker to periodically launch this attack. So, but with this ceased communication for 60 seconds, we can limit the adversary to forge one successful packet every 6 months. So that's already good for the applications. And in order to avoid the potential denial of service attack, they need to verify this packet in a very strict order. They verify this first in this order. So, but in the protocol, the FCS and ICV is completely insecure, so it's forgeable. The only security is in the MIC here. The scheme they adopted is they update the sequence counter unless the MIC is validated. But this is problematic since an adversary can intercept a packet with a valid TSC. Then it can modify the packet since these two are forgeable, so it can modify the packet. Then finally the packet will have valid these two values, but these TSC are also valid, but this MIC is not valid. So it will send out the modified packet twice in 1 minute. The system will down. They are updating this TSC after the MIC is verified. But we are proposing the solutions. It's very tricky. Just update the TSC before the MIC is validated. So if we update TSC after the MIC is verified, that means if the attacker might got a message with some effort, it's not so easy. But once it got this message, it can resend this message again and again and to block the system. So if we update TSC before this is validated, that means once I got this message, I update the TSC. Then I will verify the MIC. So the message can be only used twice. I think the reason they want to update TSC after MIC is validated is what happens if an adversary modifies TSC to an extremely large number. I send out a message with an extremely large number of TSC. Then you update your TSC to this number. Then every other packet with a small TSC will be discarded. But this is not a problem here actually, since change TSC will also change the encryption key. The TGi has some key scheduling algorithm to mix the TSC into the encryption key. So if we show some confidence in the TGi key scheduling algorithm, this will be not a problem. But this is a mitigation but not imitation, since the adversary spends some effort to get this message. It can periodically do that.
Should it always be trivial to, if NIC failures cause some kind of whatever big problem, blow up, it should always be easy to send messages with bad NICs. Right? It's really easy to forward and validate.
Yes. Yes.
So can't the adversary just always send messages and make up a bogus NIC?
No, but the TSC must be valid. That means it's not so easy to get this. Since you need a valid TSC, and the TSC is mixed with the encryption key. If you didn't break the encryption scheme, you change the TSC, that will be not valid.
You can't simply replay the previous TSCs that they...
No, you can't. So in this way, the adversary have some difficulty to get this packet, but once it got it, it can use it again and again.
Well, so I understand. You get the packet with a valid TSC.
Yes.
And the TS and now we can change the NIC. Oh yeah, we change the NIC on.
Yes. No, they cannot. He cannot change the NIC.
We change the NIC now in invalid NIC. Right?
Yes.
Is the TSC now invalid for it?
Yeah, TSC is valid. No, TSC is valid.
Okay, so the only thing that's verified is the NIC.
Yes.
The TSC and the NIC are both verified, but the TSC
is before.
The TSC can be replaced.
No, if it's replayed before we verify the NIC, this method is discarded since TSC is not valid. TSC should be monotonically increasing.
Okay.
Since they have the countermeasure for this NIC failure, the NIC is not strong enough, so they have countermeasure, which is if two NIC failure occurs, they will save the connection for 60 seconds.
Right. So if I can increase the TSC.
Yes.
To whatever I want, right? And then have a bad NIC on, right?
No, if you increase the TSC, that's this. Yeah. If you increase the TSC, then the encryption key will not be valid. So the message will be decrypted incorrectly.
Yeah,
that's the whole point
all
here.
I want to do is produce something with a NIC that doesn't check. Right?
Yes.
And this is a dot type, right?
No, that's oh yeah. If you consider the computation power, that's an exhaustive attack. But you need to send a lot of this message. But for this NIC failure, in 1 minute, I only need to send 2 messages.
Yeah. Yeah. So it's just a standard trade-off. I mean, if I check everything and somebody else could send a bad packet, then of course, fool the guy didn't even know about the bad packets. I mean. Yeah.
But the problem for this, if these 3 values are bad, then I will just discard the message silently.
Right. So all I need is 1 packet that's good.
Yeah. But the NIC is bad.
Yeah.
Everything else is good, but the NIC is bad.
Yeah.
So it's difficult for the adversary to get this packet. It's much more difficult for the adversary to get this packet. Yeah.
Okay.
Maybe we can go to it later. Yeah. There are also many other attacks found by other people on the previous 802.11 network, which is target on the management frame. I won't talk about the details of them, but in 802.11i, we can just ignore the vulnerable messages or simply drop it to eliminate the vulnerability. But there is only 2 messages left, which is the de-authentication and the de-association problem. Okay.
But looking at how weak the code is, aren't you gold plating a UCO?
Excuse me?
Aren't you, putting lots of extra features on something that doesn't deserve any respect?
Oh no, this deserves it. I assume you are talking about this micro.
Yes.
Okay.
It's not worth much, but why bother to fix something as broken as micro?
Yes, they want to reuse the legacy device, so they just design this mic with only 20 bits. Yeah, so the good news is this will be replaced by a stronger algorithm later. For the management frame attack, the 802.11i can eliminate most of them, but there is two left, which is the de-authentication and disassociation frame. Since it seems the only way to remove this attack is to authenticate this frame. So another problem with 802.11i is the failure recovery problem. Failure recovery is very important for large protocol, since it will affect the protocol efficiency, and it will, if we have a good failure recovery mechanism, it will make the derived service more difficult. So 802.11i adopts a very simple scheme. Whenever a failure occurs, it will restart from the very beginning. So this is obviously very inefficient. So how about can we restart from the nearest point? This is the intuitive thing. But there is a trade-off here. Since an access point can, if we restart from the nearest point, and malicious access point can capture this user. So this we call the captured derived service attack. On the other hand, if we restart from the very beginning, if the adversary can drive this protocol to that point, then it will waste a lot of time. So that will call it a defensive derived service attack. So it depends on the assumptions of the adversary's capability and the network scenario. Fortunately, there is a better failure recovery scheme for 802.11i. If failures occur before 802.1s, this is the authentication. So before the authentication finishes, we will just restart everything. But if it happens after the authentication, then we will restart from the nearest point. This is a better solution since we have some confidence on the authentication. If it's authenticated, that's not the malicious user. Yes.
So you see that you got 1x authentication that's going to populate your PLK cache. So automatically you restart. When you reassociate the cache, you probably use the forward.
Yes. If you are configured to use this, yes, that's true. Yes, but for mobile users, if I authenticate it with one access point, then move to some other session, then there will be some problem. But since the channel scanning time is much greater than the protocol execution time, that's not so severe here. So let's summarize the insecurities we found. So we have found the insecurities in the components like the forward handshake and the TKIP micro countermeasure algorithm. When we combine the protocol together, we found some problems in the security parameter negotiation. And we also found the inefficiency in the failure recovery. So in order to address all of these vulnerabilities, we propose an improved version of 802.11i. Okay, the improved version. We use different failure recovery, and we do authentication, then do secure association. So we have found some insecurity. We have proposed a solution, and we have got an improved 802.11i. Can we say is it secure? No. Or if I said, okay, I think hard about it, but I cannot find any attacks. So do you believe this is secure? I think probably not. So the problem is we need to conduct a proof for the security. I won't talk about too much details about the proof, but I will just briefly overview it. The proof of security is very necessary since the hard scratching approach is inconceivable. And so I think can we use finite-state verification to prove it? That's not the case. Since even a protocol passed all the verification processes, we cannot conclude it's secure because it depends on your coding and the abstraction of the protocol. So also, proof of security is useful since during the process of proving the security, we found more attacks. And when we fixed more attacks, we come back to the proof. So there are some interactions between the proof and the finding bugs. But this is a difficult problem. How to model the protocol, how to define security, how to prove them. Fortunately, there are already some formal methods to do this, like the band logic and the inductive method in Python, and the strong and the symbolic analysis, or from the process calculus. But all of these methods are not suitable for 802.11i, since 802.11i is too large and it has complicated control flows. We will use a conversational logic to deal with it. It's originated from Mitchell's paper in 2001. So, sorry, I don't know what's wrong. So,
Probably a microphone problem.
Okay. So we need to solve. So here is a figure to show the intuition of the protocol logic. If Alice wants to talk to somebody, then Alice has its private data, and it knows its private data. It knows it's running some protocol with Bob, and it knows it sent some message or received some message. But these messages might be sent from honest principals or attacker. So we need to abstract the protocol based on a WLAN model. We assume the black box cryptography, which means there is no partial knowledge in the system and there is no statistical test. The only way to break the cryptography function is to have the key. We need a language for protocol description. The previous address and message language I used in this talk is informal. So we use a code program for each protocol. We also use semantics to define how the protocol is running. And we need some protocol logic to state the security properties. And finally, we need a proof system to prove the property. Here is the example to show the code programs for the four-way handshake. This is the code program in the authenticator side. The authenticator side just do the following program. We consider the protocol is just like the following program. So here is the condition we want to check. The precondition is X and Y are the entities in the protocol. The precondition are X has PM key, Y has PM key, and anybody has PM key will be X or Y. So the security properties we want to check is first the security key agreement, which means if X is honest and Y is honest, after the four-way handshake, they will have some shared PT key. And we also use we also check the security property of session authentication. By authentication, we define it as if I can match all the message together in order, in a strict order, then I believe this session is correct. So we prove all the properties for each component. Then after we prove them for the components, we need to combine them to prove the property of 802.11i. In order to combine them, we use some invariants. Composition, I want to emphasize on this composition. The composition is very useful, not only for proving things, but actually we are following these rules when we build systems. We build several components, then we combine them together. So we need to ensure that they will combine in a secure way. The two requirements of this is, first is non-destructive combination. Second is additive combination. This is just simple. we use invariants for every component to assure the composition is safe. That means in order to compose them safely, the invariance of one component must be satisfied by any other component. We have proved the following properties. This is for every component, we prove the session authentication and the key agreement. Then we prove it composes safely.
So these proofs tell you nothing about that.
Actually, we have there are some difficulty in deal with the derived service. But for the pure memory derived service, we can deal with it. We cannot deal with the computation derived service attack. Yes.
Sorry, what's your
memory derived service. That means if you store something and store it again and again, then we can check it.
I think also the denial of service of messages on the wire, so that you simply never run through the protocol.
Yes.
Yeah, don't cover that. Because there are also subtle distinctions between levels of denial of service. I mean, obviously, the microwave oven attack, are you allowed to put the pin on an individual message, or are you allowed to certain messages?
Yes.
Or the model, so I assume you don't.
Yes, that's true. So for the details of the derived service, maybe we can discuss offline. Yeah, let's move on first. So actually, the proof is tedious, and we do it manually, but it can be automated, so it's not a problem. Now we can answering the question: can we build a secure wireless local area network with 802.11i? Basically, the answer is yes, but there are some limitations. First, security only means mutual authentication and a secret key. Second, if we assume CCMP is secure, we have data confidentiality and integrity. And we also need to assume the perfect black box cryptography. And we need to assume that legitimate entities are honest. And this is only from the perspective of the protocol. We don't consider what's the implementations. If there is some software bug or there is some buffer overflow in the implementation of the protocol, then that might be cause insecurity. And we don't consider the other mechanisms in the system, like how do you implement a firewall, IPsec, and SSL application, and so on. But from the perspective of the protocol, it's secure. So finally, we go to the conclusions. We did these things, use the finite-state verification to verify the components, and we found that some attacks on the protocol, and we prove it's really secure. So now we can build a secure wireless local area network. An interesting or natural problem is, can we build a secure ad hoc networks from this? I will not touch that topic in this talk, but if you are interested, maybe we can discuss offline. I will stop here, and I will be glad to take any questions from you. Of course, after I use these figures after such a talk, I think I will be very glad to receive any questions in a wireless way.
Why did you verify this protocol manually if it can be automated? What was your
the proof system, you mean?
Proof,
Yeah. The proof system is based on some axioms, like if I receive the message, example, if I receive the message which is signed by somebody, so then I will know this message is come from that body. If we assume that person is honest, it will not disclose its private key to others. We use this kind of reasoning. So any other questions?
Any other question? Thank you.